Welcome and hello. This is a video exercise using the FHWA hydraulic toolbox, and I've titled this exercise Minimum Channel Diameter. So we're going to be using the channel calculator as well as the rational method calculator to obtain the peak flow rate. All right, so what I have on the screen is my hydraulic toolbox. I'm going to put the problem statement up on the screen. Here you see it. Find the minimum channel diameter, D sub min, of this semicircular channel right down here. Now, the channel data is provided, such as the Manning's N, the longitudinal slope, and FB sub min is the minimum freeboard. So we need to maintain at least 2 feet of minimum freeboard. To determine the flow rate through this channel is also going to be a large part of this exercise, and we're going to determine that using the watershed data and the rational method calculator. So as you see, we have a bunch of storm/watershed data provided. So let's go ahead and get started with the channel calculator first, and then later we're going to have to use the rational method calculator. Okay, back to the toolbox. I'm going to click on Project, right-click, New Channel Analysis, and then double-click to open up this calculator. What we know from the problem statement is that the shape is circular, specifically semicircular. So even though it says pipe diameter right here, we're really just using the bottom half of a circular shaped pipe diameter. So the bottom half representing a semicircular channel. All right, so for the diameter, we actually don't know this. In fact, this is the parameter that we're trying to solve for. So we're going to come back to this and test out some numbers. But for the meantime, we can fill out a few other fields here in this calculator, such as the longitudinal slope is 0.015, which is 1.5%. And then the Manning's roughness value, we were also given that as 0.013. All right, down here, enter flow or enter depth. If we knew the pipe diameter, we could just enter the depth as half of that diameter minus 2 feet. We don't know that, so we really can't approach this problem that way. So what we're going to do is enter the flow rate right here, and we don't know that flow rate either at this time. So we're going to have to pause our activity in the channel calculator and then come back to it once we know the flow rate, which is what we'll determine right now. Okay, so click OK. Next, I'm going to come up to the project and go right-click, Add New Rational Method Calculator, then double-click to open that up. We're asked for the runoff coefficient, the area, and the rainfall intensity. Ultimately, that will calculate our peak flow rate right here, which is what we'll use back in the channel calculator to ultimately determine that minimum allowable diameter. All right, so let's get started with these input data. We have the runoff coefficient C and the area. Back to our problem statement, we have a total area of 85 acres, and that's composed of 15 acres residential suburban and 70 acres unimproved area. So we know the total area is 85 acres. We'll add that to our calculator in just a moment. But while we're here, let's go ahead and determine the runoff coefficient. I've changed over to the HEC 22, the Hydraulic Engineering Circular number 22 document. This is table 4.1. We have a list of different runoff coefficients based on the land use category and the type of drainage area. I'll leave a link to this document to download if you're interested. I'll leave the link in the description. So what we have is two different types of land. We have residential suburban and unimproved area. So back to that table. Here's suburban, 0.25 to 0.40. So that's a range of different values for runoff coefficient. And then further down, we have open as the land use and then type as unimproved area, which ranges from 0.1 to 0.3. So without any additional information, I'm just going to use the middle number that splits the difference between the min and the max for both of these different land uses. So for suburban, I'll just select 0.33, and then for unimproved area, I'll select a C value of 0.20. After doing the math, I've got a quick table here that shows the two different land uses, and then this bottom row is combined. So we have a total area of 85 acres, and then the weighted average for that C, that composite runoff coefficient, calculates to 0.223. So I'm going to go back to the calculator now. I'm going to go to 0.223. The area was 85. Oops. Okay, so it looks like we're dealing with metric units. Let me go ahead and switch that back. Okay, so let me just cancel that. I need to switch to US customary units, rational method, okay? 0.223, and then the area in acres is 85 acres. All right. Next is the rainfall intensity. So we were not provided the rainfall intensity directly, but we were provided some other information which can help us determine that rainfall intensity, such as the area is located in Dallas, Texas. The recurrence interval is 100 years. And to find the time of concentration, we're given this shallow concentrated flow information: top elevation, bottom elevation, the length, and then the type. So let's get started on that. I'm going to click on the compute button right here. And then since we know it's Dallas, I'm just going to use an IDF curve for Dallas. I'll click this radio button for user supplied data and then click on get NOAA Atlas 14 data. By the way, there is a side note here that says that the IDF equation is given in US customary units. And in preparation for this exercise, I tried getting NOAA Atlas 14 data when using metric units, and it just wasn't coming up. So if you plan to use this particular feature, you're going to want to be using US customary units. At least that's my experience. All right, so if you happen to know the lat long of Dallas, you can just type that in here. I don't, so I'm going to click on this button to select the lat long from a map. And then here is the map of Dallas. That's just because I've already searched Dallas before. But anyway, you can zoom out. You can type in your own lat long. You can actually type an exact location and then click the jump to button, or just zoom in, pan around, and zoom out, whatever. As I'm zooming and panning, the latitude, longitude is updating. So what I'm going to do here is just center myself on Dallas, wait for the image to resolve, and then click on this OK button in the bottom right corner. That should save my 32.76 north latitude and 96.784 west longitude values into the form right here. Okay. So with that data saved, if I click OK, give it a moment, and then the numbers should show up. All right, so there they are. These are the rainfall intensities for Dallas, Texas, for the specified recurrence intervals and storm durations ranging from 1 year to 500-year storm, and then the duration from 5 minutes up to 24 hours. Now, our storm is the 100-year storm, so I'm going to click on this 100-year row in the table. That will update my IDF equation where we're solving for the intensity based on the time of concentration. Now, we don't have an exact time of concentration. If I knew it was 10 minutes, I could just compute the intensity, or 30 minutes, compute the intensity. Problem is, I don't have that information, so I'm going to have to click on compute T sub C and then define the parameters. We have sheet flow, shallow concentrated flow, and channel flow, all of which will contribute to our total time of concentration. From the problem statement, all we're provided is shallow concentrated flow. And then here are the numbers that we're going to use. And because this is the only information we're provided, this is the only data that I'm going to use when calculating the time of concentration. So I'm going to uncheck enable for both sheet flow and channel flow, and then fill out the fields here. We have a top elevation of 250, a bottom elevation of 200. The length is 2,100 feet. And then this K value, there's a table in the user's manual for this K value. It's on page 35 right here. And it's also originally referenced in the FHWA HDS2, which I believe is the highway hydrology document. So for the different land cover / flow regimes listed here, we have the corresponding K value that we're going to be using in the calculator. So for the grassed waterway, which is what we were given, we want to use a K value of 0.457. So 0.457. Very cool. And then we should be good. So as soon as I tab off, it calculates my time of concentration at 15 minutes, just over 15 minutes, 15.04 minutes, and I'm good to go. So I'm going to click OK. That time of concentration has appeared right here in the form, 15.0 minutes. Now, if I click on compute intensity, okay, it looks like it's already computed. I now have a storm intensity of 8 inches per hour for my 100-year storm in Dallas. Now we have all we need to compute that peak flow rate for our channel. And I'm going to click on done. So we have a peak flow rate of 151 CFS, which is what we're going to be using in the channel calculator. So I'll take 151, click OK, reopen the channel calculator. And then for the flow rate right down here, 151.8 CFS. We have our longitudinal slope and Manning's roughness from before. Now we need to identify what is the pipe diameter. So keep in mind, we want a freeboard of at least 2 feet. That's the minimum freeboard. So we're looking for the minimum diameter such that radius minus the depth equals exactly 2 feet, 2 feet of freeboard. All right, so just as a first trial, I'm just going to type in 12 feet and see what happens. And we will definitely have to adjust when we click on calculate and look at the depth is 1.754 feet. Okay, so our pipe diameter is way too large because half of 12 feet is the radius, which is 6 feet, and 6 feet minus 1.754 feet would be 4.246 feet. And we want that number to be 2 feet. And so we have way too much freeboard, more than twice as much freeboard as we want. Let's go ahead and try a different number for pipe diameter, or I should say semicircular channel diameter. Let's go with 8 feet. Just throwing out a number, tab off, click on compute. Now the depth is 1.992, which is surprisingly good because half of the diameter of 8 feet is 4 feet, minus 1.992 is pretty much exactly 2. It's just barely over 2. Okay. I expected it to take more than 2 trials, but I guess I kind of got lucky. So we have a pipe diameter of 8 feet, which means we have a radius of 4 feet and a depth of 2 feet. All right, well, that was it for this exercise. What we did was use the channel calculator and the rational method calculator and the FHWA hydraulic toolbox to determine the minimum diameter size for a semicircular channel to convey the flow that is runoff from a 100-year storm in Dallas, Texas.